Section 6-2, addition, subtraction, and estimation with rational numbers. Let's start by looking at like fractions. Like fractions are fractions that have the same denominator, meaning they represent the same portion of the whole. When we have like fractions and we want to add them together, we simply just count the number of parts, which is really just the numerator. So we're really just adding the numerators here. I've got 3 different representations for adding like fractions. It's the exact same numbers being added together, but visually we're representing them different. So in the first visual, I have the fraction 2/5. I'm adding that to the fraction 1/5. And I can tell that those are the fractions I'm adding because when I look at the circle, which represents one whole, I can see that there are 2 pieces shaded in out of the 5 pieces that makes the whole. So I have 2/5, and then similarly the 1/5 fraction is 1 piece shaded in out of the 5 parts of the circle. And when I add these together, I like to think of this as combining leftover pizza. So if you had bought maybe a cheese pizza and a pepperoni pizza, you had 2 slices left from your cheese, 1 slice left from your pepperoni, you wouldn't put each of the separate pizzas in the separate boxes, probably. You would like to combine them, unless, you have reasons to not combine meat with the non-meat pizza. But most people would probably try to combine them into one box to put in the refrigerator. And so you would just slide all of the leftover slices into one box. And that's kind of what we're doing here. We've got the yellow pieces combined with the orange pieces, and we're able to combine those into one circle. Notice that the yellow and the orange pieces are the exact same sizes, which is why we're calling them like fractions. When we add them together, we can just count that we have 1, 2, 3 parts shaded out of the 5 parts that we would need to make a whole circle. We can also use rectangles that are partitioned to represent the same addition. So we have 2/5 represented using 2 shaded portions out of the rectangle, and we have 1/5. Adding them together, we're simply filling in the pieces that we have. So we see the 2 yellow pieces, the 1 orange piece, and the fact that they're different colors doesn't matter because when we add them together, we just count that we have 3 shaded pieces out of the 5 that we would need to make a whole. We could also use a number line. We have an arrow on the first number line to represent 2/5, an arrow on the second number line to represent 1/5. When we add them together, we just join the arrows tip to tail. So our first arrow takes us up to 2/5, and then our second arrow continues us 1 more 5th so that we land on 3/5. So no matter how we like to visualize the problem, we'll get the same answer. If we wanted to look at this in a general sense, we could say some fraction a over b plus another fraction with the same denominator, but probably a different numerator. When we add those together, we're just adding the numerators and copying over the denominator. Remember that the denominator represents the number of pieces that it requires to make a whole. When we're adding fractions with the same denominator, we are not changing the size of the piece whatsoever. We're just counting how many of those pieces we would like to consider. Sometimes we're looking at unlike fractions. These are fractions that have different denominators, and when we try to combine them the same way that we did with like fractions, we see a problem. For example, we have our circle representations of different fractions. In the yellow, I see that there are 3 pieces to make a whole circle, so I know I have a denominator of 3. 2 of those are colored yellow, so that first circle represents 2/3. In our second circle, I can see that this circle has been cut into 4 pieces. So this denominator should be 4, and only one of those pieces is shaded in orange, so I know I'm talking about the rational number 1/4. When I try to combine those shaded in portions the same way I did with the leftover pizza, notice that the yellow and the orange are different sizes. And the piece that's left over is another different size. So we have 3 different size pieces inside of this one circle. Now, we could take a guess at how much of this circle is shaded in, but we don't like to guess in mathematics. We like to be more precise, especially when we use mathematics for important things like building bridges. So let's focus in on the problem here. The problem is, I don't even know what to write as my denominator for the slices in my sum. So let's deal with that first. If we look at the yellow slice and the orange slice, we can see that they're different sizes. But maybe it's possible to cut a yellow slice and cut the orange slice so that we actually do get the same size slice. Maybe I try cutting each one in half. If I cut the orange slice in half and I cut the yellow slice in half, those look closer in pieces, but if I continue this pattern, I'll notice that I still have the same problem. Those denominators don't match. The orange slices would look like I need a total of 8 to make a complete whole, and I've got 2 of those shaded in. The yellow slices look like I need a total of 6 to make a whole, and now I would have 4 of those shaded in. So simply cutting each slice in half is not going to make them match. Maybe instead of cutting each one in half, I do something like cut one in thirds. If I continue this pattern, I need to count what my denominator would be. So if I have 4 slices and I cut each one of those into 3 slices, that would make a total of 12. And then in this case, I have 3 of those 12 slices colored in. What about in the yellow? If I have 3 parts to make a whole, can we think of a way to turn that into 12 parts to make a whole? What if I cut each of the 3 parts, each one, cut it into 4 parts? If I continue this pattern, I'll end up with 12 slices to make a whole. In this case, when I make it into 12 slices to represent a whole, I now need 8 in my numerator. If we divide up our circles this way, then we are talking about like fractions. So instead of 2/3 plus 1/4, we could use equivalent fractions, 8/12 plus 3/12. So now let's answer that question. 8/12 plus 3/12. Well, now we're talking about like fractions. We just combine all of our colored in pieces into one circle, and we can see that out of the 12 slices in our sum, there are 11 colored in. This idea is basically called getting a common denominator. So if you have unlike fractions, the first thing you need to do is turn them into like fractions by finding a common denominator. Often we try to find the least common denominator, but it doesn't really have to be the least common denominator. You could have bumped both of these up to a denominator of 24, but you would have had 22 for your numerator, and then you'd want to simplify that. But the important part is that we need to find a common slice or a common denominator so that we can count equal size pieces. We can do the same thing in any one of our visual representations of these fractions. So if I were instead using a rectangle diagram, I would still make the same number of cuts. So remember that we took the yellow pieces and cut them into 4 pieces. And we took the orange piece and cut that into 3 pieces. That way, both rectangles are now cut into equal sized parts. There's 12 of them that make a whole. And then we copy that into our solution. And we can see again that we have 11/12. In the number line model, it's not as clear that we have different size pieces, but it is clear that if we stack our arrows tip to tail, that the end does not land on a perfect grid point, no matter which of the grid points that we're using. So we would have to do the same thing, where we divide the thirds into 4 pieces, we divide the quarters into 3 pieces, or in the end, we're basically finding a number line that goes from 0 to 1 that has 12 pieces on it. And then we're counting how many of those pieces we have. The yellow arrow, if we were to divide it into 12s, remember that was 8 pieces. And then the orange arrow, when we divided that into 12 pieces, that was 3 more. That would stop us at exactly 11/12. So when it comes to adding fractions, whether they're like fractions or unlike fractions, the goal is to count equal size pieces. So if you already have equal size pieces, go ahead and just count them up. If you don't have equal size pieces, you need to find equal pieces. So if we wanted to generalize this, we're saying that we're adding a fraction like a over b plus another fraction like c over d. Notice that the denominators are different. A guaranteed way to get a common denominator is to multiply the 2 denominators together. And we essentially did that here. Remember that our original fraction was 2/3 plus 1/4. If you multiply those denominators, you do get 12. So you would multiply your denominators, and then not only would you multiply your denominators, but you would need to multiply the opposite denominator to each numerator. And that's because finding a common denominator is using that law of fractions, where if I want this fraction to have a denominator like BD, I need to multiply the numerator and the denominator by D. And if I want the other fraction to have a denominator like BD, I need to multiply the numerator and the denominator, by B. So if my common denominator is B times D, then my numerator would become D times A plus B times C. Now, if BD is the least common denominator, then that makes work a little bit easier for you. If it is not the least common denominator and it's just a common denominator, a common multiple of B and D, then you're going to have to reduce the fraction at the end. And you might have to reduce the fraction when you're dealing with the LCD as well, but I can guarantee that if you don't do, I shouldn't guarantee it. Least common denominators can possibly save you some work, but sometimes you still have to simplify it after that.